Welcome back to this NPTEL online certification course in molecular rearrangement and reactive intermediates. In the last couple of classes, I was talking about the radical chemistry. I talk about the different type of method of generation of radicals and their different type of name reactions. In the today's class, I decided to talk about some of the single electron transfer reaction. So in the today's class topic, I am going to talk about the reduction using metal based reducing agent. So I am going to talk about a lot of the single electron reduction using the sodium, potassium, magnesium, and then also the acylon condensation, another very important name reactions. Then the Bauer blank reduction, and then finally the very important Bartsch reduction. So before I go to all these different chemistry, first I want to start with this the basis of this metal reducing agent. What is the general reactions and how this reaction happens, and generally you can see that there are number of metals at the zero or low oxidation states. We are talking about some sort of a the like a metal like the sodium, lithium, those and in the potassium, okay, and you can see magnesium, zinc. We're going to talk about some titanium, samarium. So you will see that in a separate class we're going to talk about some of the reaction of samarium. So here what is happening, these are low valent metals, so which can give a single electron, and then so it's actually act as a reducing agent, okay, and then you can see several different type of chemistry. So these are called electron transfer agents, okay. So what is the mechanism in presence of a proton source? If you have a proton source, then what is happening, the metal first is giving one electron to this q, okay. So that is becoming a q dot minus and m plus. So this is a radical anion formation happening, and after that you can have a if you have a H plus and X minus, then the H plus is now take the H plus and then it is become QH. So it's a radical with the proton with the Q. And if you take one more electron from this from the sodium, then it will become a Q minus H and M plus, correct, because now your sodium will be plus, which can take another HX to form the QH2. Or if you have electrophile, then it can become this Q E and H. Of course, we are going to talk about several different electrophile in the class. If you have a aprotic solvent with a leaving group, then what is going to happen? Of course, now you are starting with QX. So here you started with a QX because X is a leaving group. Again, if you give a single electron, it is going to become what is going to, there will be a heterolytic cleavage of this QX. It become here you can see there is a radical anion going to form here, and now you can form a literally it's a Q dot and a X minus. So as I said, there will be heterolytic cleavage, and then if you give you one more electron, then the Q dot will become Q minus. It will take a proton at the end to form a QH, or if you take electrophile to become QE, okay. So these are the two different scenario I am going to explain you. One case you have seen that there is no leaving group, one case you have a leaving group like a QX. So let's now come to a real example. So the first reaction I am going to talk about is acylon condensation. It's a bimolecular. So I think every single term is very important here. This is a bimolecular. That means two of these ester going to form a bond. Then this is a reactive coupling. That means there is a reduction happening. We are going to come back to that between two carboxylic esters, okay, and it's formed one important compound. One is alpha hydroxy ketone. So you started with this, so this is a bimolecular reactive coupling between two carboxylic esters, okay, in place of molten sodium in excess and xylene in reflux, and then you coincidence the reaction, you forming a very important compound called alpha hydroxy ketone. So let's try to understand the mechanism. So before I go to the mechanism, one thing we should try to understand that when you talk about that where this single electron transfer is happening. Suppose if it is trying to reduce this carbon oxygen bond, then where the single electron is coming in? Of course, the single electron is given to the corresponding LUMO orbital, but before that we will try to understand that suppose if you have a carbon-carbon bond, let's try to understand why. So we are going to really try to focus on this first step, that once you have this ester and once the sodium gives single electron, you end up forming this carbon dot and oxygen minus. Why this is happening? Of course, in the textbook you might say, sir, this oxygen is electronegative, more electronegative, that's why oxygen will be the minus and then carbon will be the dot. But how this is coming into the picture? So if you try to understand that particular thing, you have to go to the bonding of the sol. If you think about carbon-carbon single bond, then you know that this is a carbon, so this is a, So 2 of the carbon forming a bonding and a anti-bonding, correct? So of course they have a bonding electron, and we can say this is a, this is a bonding and this is a anti-bonding. And one of the important thing is these 2 carbon are actually in the same energy. But once you have a carbon and oxygen, then because oxygen is more electronegative, it's going to stabilize it. So now your oxygen is here and the carbon is here. Now if this is your bonding, anti-bonding, or the homo-lumo, whatever way you want to say them, and if they are forming a bond, okay, now if this is your bonding and this is your anti-bonding, then if you, or your homo, then your homo of this bond actually close to the oxygen, not the carbon. Okay, so that is a very important thing here. That's why, because when you are giving one more electron, so the electron coming from sodium to the corresponding anti-bonding orbital. Okay, so that means you can clearly see the homo is close to the oxygen, the LUMO is close to the carbon. Okay, that's why after the first reduction happen, you see oxygen have 2 electrons, that's why the O minus here, and then carbon having this dot. Okay, I think you understood the this part now. So now what is happening? This is a bimolecular reaction happening. So sodium is reducing the ester, forming this C dot O minus. There will be another one, another ester also going to, after a single electron, after taking 1 electron, it is going to form that. So now 2 of these can form a dimer. We already talked about that, the radical can form a dimer, correct? Radical dimerization is a reaction which I have already discussed before. So this is a dimer formation happening first. Once the dimer formation happening, next thing is you have a leaving group here. You have this, so now if you see there is a O minus and OR. Every carbon you will see O minus OR. So this O minus is going to come back and get rid of this OR. So you can see in this particular step, 2 equivalent of alkoxide is actually coming out. We are going to come out that in the next slide, after 1 2 slide, I am going to explain there is a problem with that, because you are generating 2 equivalent of alkoxide that can do other side reaction. But again, once you form this 1,2 dicarbonyl compound, the reaction is not going to stop here, because your carbonyls are even going to take the single electron from the sodium and going to reduce further. So it is sodium will going to give 1 electron here. In both of these carbon going to form the dot here, which can form this compound. In the acidic workup, finally you come to here, and then after the tautomerization you will going to form the corresponding alpha hydroxy ketone. Okay, so from first thing is the dimerization, formation of the 1,2 dicarbonyl compound, 1,2 diketone, further reduction to the alpha hydroxy carbonyl compound. Again, here is an example here. Mostly you will see these reactions are going to used for formation of the ring. You have 2 esters here. Okay, they are participating in acetylene condensation in place of sodium and xylene, going to form this compound here, which is again you can see this is a alpha hydroxy carbonyl compounds. Okay, you are forming at the end. Again, if you see the mechanism, very similar mechanism. First thing is the reduction of the ester with a single electron, forming a C dot and O minus with Na plus. Again, very similar thing happen. Then the radical going to recombined. After that, this alkoxide going to get out from here, and then this again this 1,2 dicarbonyl compound. Again, the sodium is going to transfer 1 more electron. So 2 of the sodium going to transfer 1 electron here to reduce them. Then finally, after the protonation, it's going to end up forming this corresponding product. Okay, so you can see there are several example. I just include one example here. You can practice more and more example in the literature. Another important example here, you can see there is 2 esters. Now they are, you can see so these 2 esters again going to take part in the acetylene condensation in place of sodium and liquid ammonia, and in place of diethyl ether, what is going to happen? You again end up forming this alpha hydroxy carbon compound. I think the mechanism already have discussed. Very similar mechanism happen. First single electron transfer to form C dot. The radical recombination, get rid of the alkoxide, 1,2 dicarbonyl formation. Then further reduction can form the corresponding alpha hydroxy ketone, which can be finally converted to the estrone. And then I think I already talked about that in this reaction you are getting rid of 2 alkoxide. Again, alkoxide are strong enough, can able to deprotonate. That means if you have a alkoxide base in the medium which is coming out, it can able to deprotonate from the ester. Okay, so the alpha, this proton which is alpha to the ester going to get deprotonated, and that can, you can write some sort of O minus, and so you can, after this ester, you can see there will be a double bond O minus OR, and then this can come back, and now this enolate can attack to the another ester. So this is the intramolecular cyclization called Dickmann's condensation. So this can happen. So this can be a byproduct in this reaction, okay, because you have a two equivalent of alkoxide base are coming out. So to stop that, they found, okay, what about if you can, if you don't use alkoxide, or we use some other way to get rid of alkoxide. I think the other way is that how to remove alkoxide ions from the medium. That is the technique they used. They want to get rid of the alkoxide using TMS chloride. That means once you have this ester here, you are using sodium and TMS chloride. Now what is happening? Your intermediate is now becoming OTMS. Okay, and so then what is going to happen? Then if you use the H3O plus and methanol, it is going to form the corresponding alpha hydroxycarbon compound. Okay, so here what is going to happen, that you are removing the alkoxide ion from the medium by using TMS chloride. Okay, so that is one of the tricks you can use, so that now you have this OTMS formation happening, which can be easily going to form the corresponding alpha hydroxycarbon compound. Again, there is an example here. Of course, you are using now the TMS chloride. So you have this, you are forming this corresponding OTMS here, which can be going to form this the bicyclic ketone here. Here there is another example. You have the sodium and TMS chloride. Okay, so that can again you can form this very similar intermediate here, the OTMS. And now if you don't quench here, you can isolate in this stage, but now if you use a H3O plus, you end up forming the corresponding alpha hydroxycarbon compound. Okay, so now I'm going to talk about, I think if you've seen in the previous slides what I was talking about, that in this reaction, when you performing the acetylene condensation, if you have a protic solvent. So in the previous case we talk about, always if you see in the reaction we talk about xylene. We have not talked about any type of protic solvent. We talk about xylene with the molten sodium, and then of course once the reaction is over, now you are quenching with the the H3O plus to get to the product, correct? But the question comes, if you use ethanol in the solvent in this reaction, what is going to happen? Because if there is alcohol present, then you, instead of forming the corresponding alpha hydroxy ketone, you end up forming a corresponding alcohol after the reduction of the ester. So this will be a reduction of ester going to take place, and that is called the Bauer-blank ester reduction reaction. Okay. So now we try to understand the mechanism of this reaction. Of course, we know the first step from the previous acetylene condensation. The sodium is transferring a single electron, and after that, what is happening? If you have ethanol, then instead of the dimerization, it will move this direction. Okay, it will take the H plus from the ethanol, it will form this compound with the carbon dot here. Again, it will take one more electron from the sodium and going to get to the, you can see it is going to form a minus here, which can take a proton from the ethanol. Now you can see this carbon have a OR and a OH, so you can clearly understand this will not stay here, it will immediately going to convert to the corresponding aldehyde. Okay, and now the aldehyde is going to get further reduced with sodium, so it is going to form the O minus and the C dot, correct? And then you can have a ethanol can give a H plus to make the OH. You have a C dot. Now the sodium can give one more electron to become a minus, and then once you have ethanol, it is going to form the corresponding alcohol. Okay. So you can see here that if you have a ethanol, then what it is stopping? It is stopping the first reaction, which is the second reaction of the acetylene condensation, which is the dimerization, which is getting stopped. So you are getting protonated and getting further to convert to the aldehyde, and then all the way to the corresponding alcohol. So now we are going to move to a very important reaction in organic synthesis called Bart's reduction. So I'm going to spend a lot of time here and try to understand, what is the mechanism of this reaction, what are the different variation. Okay. So this is a 1,4 reduction of aromatic ring. So this is a very important reaction, why I say, because it is reducing aromatic ring. Okay. So this is reducing aromatic ring, and it's a, you are forming some sort of a, like, it's from benzene. What is happening? You are getting reduced. So there is a 1,4 reduction happening. Of course, you are see, we're going to come back to that. Depending on the R group, there will be a selectivity difference. Some, we're going to come back to that discussion also. And then we are saying that in this reaction, first we try to understand that the corresponding unconjugated cyclohexadiene and the heterocycles by alkali metals like lithium, sodium, potassium, dissolved in liquid ammonia. So we are taking this, lithium, sodium, potassium, dissolved in the liquid ammonia, and we have a, alcohol here, which is the source of the proton. In the presence of that, we can able to reduce the aromatic ring. Okay. It is not only be going to be like a phenyl, it can also reduce the corresponding the heteroyl. We are going to come back some of this, and the reaction, of course, the reduction occurs at minus 33 degree, which is the boiling point of the liquid ammonia, because you can see you are using the reaction at the liquid ammonia. So you have to do the reaction at minus 33 degrees to continue the reduction happening. Okay. Of course, some of the times the compound have a problem with the solubility ammonia, then that time people can use the THA ether in the reaction as a co-solvent with the ammonia. Okay. So if you see in this reaction, if you have done this reaction, or at the beginning when you have this, the sodium or lithium with the liquid ammonia, you will immediately see a blue solution of solvated electron. So that blue color formation, if you are doing this reaction, first thing is formation of this blue color can indicate the solvated electrons are ready for the reaction. Okay. Again, then you can add your substrate and continue the reaction. But again, if you see that, if you after the some time, if you think that you will make the the blue color and then do the reaction later on, then these things not stay for a longer time. What happen over the time, the color fades and it releases the H2 slowly. Okay, that's why it is better that once you add the liquid ammonia and the sodium or the lithium, you also start doing your chemistry. Okay. Again, I think the another important thing, I think, if you see about the reduction potential. Okay. So this is very important, because if you a 2.48 volt for the reduction of benzene. Correct. So you can see that if you have a lithium with the ammonia, then it can you have a electron volt of 2.99. So it can comfortably reduce the benzene ring, or the sodium. Okay. Or the potassium also. So they can able to reduce the benzene ring, because you can clearly see from this reduction potential values. So now if you see the mechanism, whatever reduction is happening here, that also depend whatever functional groups you have attached here with the ring. Of course, we are going to come back to electron donating group or electron withdrawing group. Okay. But first thing is what is happening once you have this sodium and the liquid ammonia, you can see these solvated electrons will be transferred to the benzene ring. So the ring will become something like this. A lot of time you will see in the textbook, they I'm going to show some of the mechanism which is mostly given in the textbook. You will see the electron is adding in the particular position and forming the dot and minus, but I feel it is better to write, because if you see literally what is happening, the electron is getting to the into the ring, and it is actually present everywhere in there. So it is actually a conjugated compounds. Correct. So you see there is a formation of a radical anion happening, and that going to take a proton from the tarbutanol here to form this radical species here. Okay. And now you can see there will be another electron going to be transferred from the sodium, going to form this anion, and finally you can see this anion will be forming next to this ester to get it stabilized. That's how it can take the proton from the tarbutanol to get to this corresponding proton. Okay. So if you see in this reaction, what is happening, where this electron is getting transferred. As I mentioned, for the carbonyl compound also, you will see the electron is getting transferred. What is happening? The single electron is going to the corresponding anti-bonding orbital. Correct. So very similarly, in case of benzene also, there is this you will see the electron is going to get to the corresponding anti-bonding. So that means now we will have a 7 electron instead of the 6, because now your electron will be in the anti-bonding orbital. Okay, so that's how it is going to reduce the the benzene ring. As I mentioned that if you have a donating group versus electron withdrawing group, again I think if you see that if you have an electron donating group can stabilize the electron density in the ortho and meta position. Okay, so if you have electron donating group that can stabilize the electron density in the ortho meta position, so there will be ortho meta selectivity. If you have an electron withdrawing group, then there will be reduction happening in the ipso and para position. So that is the important thing. That means you have so if you are trying to solve a problem on this topic, then you have to understand this, that if you have a electron withdrawing group, then it is following the ipso and para position, hydrogen going to be in the ipso and para position. That means if I have a group like this, from this, if I have an electron withdrawing group, then you can clearly going to write that okay, there will be product where there will be hydrogen going to be in this position, or you can say again both cases what is going to happen. So there will be ipso and para, correct. But once you have electron donating group, what is going to happen? Once you have electron donating group, after the reduction you end up forming this compound. So you see the hydrogen is coming in this position, is coming to the ortho and to the meta position. Okay, now we'll try to understand how these things are happening. Of course, once you have electron donating group, after the single electron transfer is happening, okay, you are forming this minus and dot. You can also write as a dot and minus. These are again, as I said, it's not that there is a minus here or dot here. It is actually it's a radical anion. Okay, so that means you already have this electron transfer to the anti-bonding orbital. But again, as I said, that if you have electron donating group, that is going to stabilize the anion. So it is going to get protonated here first, and then you can get one more electron from the sodium. This is going to make an anion here, which will take a proton and going to put a H here. So that's how you will seeing a reduction happening. Once you have electron withdrawing group, in the next case, again after the single electron, so again once you give electron, we have shown in the previous slide also that it will be a radical anion formation is happening. Again you can see, you can write this as a dot minus, or you can write as a you can write a dot here and a minus here. But again what is going to, once you form a minus, it can take a proton from your ROH. So there will be H here, then it can take another electron from the sodium from a minus here, which can take another electron from the corresponding ROH to form. So now you will see a formation of a ipso and paraselective product. Okay. So again I hope you understood this part. So let's try to do the some of the problem here. I think again if you have a methoxy, we know there will be a ortho meta. So you will see this is your ortho position, this is your meta position. So there will be there will be H on the ortho and meta position. Of course, once you have a H3O plus, what is going to happen? This is going to convert to this alpha beta unsaturated carbonyl compound. Okay, so that is so that is one very important thing, that from this compound you can easily able to convert to this compound in a one pot manner. So first do Bart's reduction, then treat with the acid, that is going to convert to this alpha beta unsaturated carbonyl compounds. Okay, so here again I think you have seen the, I think we have already discussed the mechanism. So there will be a dot and a minus, or sometime you can write a minus and dot. You can, I think you can write a minus here and a dot here also. I think either way that is same. As I said, this is not the right things to write all the time. It is actually a radical anion. We should write in that form where it will be actually delocalized in the entire ring, correct? And then a protonation first, in this position or in this position, and then the next thing is another electron coming from sodium, and then again the protonation happening from the ethanol. Okay. So here again you can see this this technique was used for further in the natural pot synthesis. So once you have these compounds, once you have this in case of the acid base, once you, so actually what is happening, if you see in the mechanistically, once you have a H3O plus, it is going to form this compound, but in case of acid and base, what is going to happen, it is going to form the more stable compound, correct? That's why it is going to get to this product, which is the alpha beta unsaturated compounds, and then it can be applied for the natural photosynthesis. Another example here, so here you can see you have this OMe here, OMe group in this ring, so it's an electron donating group. That means we know that it is going to form this the selectivity ortho meta, but now once you have a HCl and HF in the reaction, that is going to convert to this alpha beta unsaturated carbon compound. So again you have seen the effect of substitution in the Birch reduction. You have a acid, I already talked about, that is going to go for this 1,4, okay, 1,4 reduction. So that is going to be in the ipso and going to be in the para. I think I already talked about the mechanism in the previous case. I think it's followed very similar mechanism which I already discussed before. Some of the example here, now we are talking about the naphthalene. Okay, once you have a naphthalene, again one of the ring is getting reduced to get to this compound here. Okay, you can see this is a very similar to the benzene ring. You can see there is a H coming here. Okay, so again so this hydrogen is coming from the corresponding ethanol. Okay, again you can see here, if you have through this compound you have a methyl and a methoxy. Again the methoxy is going to be the one electron donating group, correct? So that is going to follow the same rule what you have learned. So it will be the ortho and meta. So is in this position you will see this hydrogen going to be attached. Okay. Again I think we have already explained that it is going to go through some of this species formation like that, and then protonation and then further reduction. Okay. And again if you have a COOH and methyl, of course the COOH will be the electron withdrawing group, so that is going to dominate. So once it is going to dominate, you will going to form the a ipso and a para. So this is the position going to get proton. Okay, so that's how you end up forming this product. Okay, again we have shown that okay, that's how going to get reduced, and then further it is going to get to the product. Another example of Birch reduction. So here what is happening in the Birch reduction, instead of alcohol, if you have a alkyl iodide, what is going to happen? Of course, if you know that first thing is once you have a sodium, it is going to give 1 electron to reduce the ring, correct? Going to form this a radical anion species, and now you have first thing is going to get a proton, and then once you have this radical here dot, that is going to take another electron from the sodium, going to form a minus. Now you can see it's a it's a stabilized anion which is going to react with your corresponding alkyl iodide to form this quaternary center here. Okay, so you have a R esters, and there is a carbon and there is a nitrogen here, correct? So that means if you have this scenario where you can add a alkyl iodide, then you can end up getting to you can also get a alkylation happening at the end. Another example here, first thing is the reduction of this furan ring, and then as you see there is electron withdrawing group on this side. So that means this radical anion will be stabilized, and that that can be alkylated with the methyl iodide to introduce methyl group here. Another example here, I think you can see in these cases you have a OMe group and you have this group here, correct? You have electron withdrawing group. Again, if you have electron with, so you can see in this in the reaction what is happening. If you use the ethyl iodide here, you see first if you have electron withdrawing group here, then that is the one which is actually dominating the, so that is actually controlling the reaction. That means we know that there will be ipso para, correct? Ipso and para position. Now in the ipso position, if you see that is next to a this carbonyl group, means once the radical anion going to form, that is going to react with the ethyl iodide at the end to form this corresponding product where the ethyl will be in this carbon, correct? And then you can see here once you have this, so at the same time what is happening, there is a OMe going to be here. Okay, so because you can see there is a ipso and the para position where there will be H here and there will be ethyl here, that is going to act. Okay, so now if you have a the PDC which can able to oxidize this position, the allylic position getting oxidized to form the corresponding carbonyl group here. Another example of Birch reduction here, you have the electron withdrawing group. So this is the ring and you have electron withdrawing group. the amide group, you have a liquid, ammonia, you have a, the lithium and the ammonia, that is going to reduce it. So there will be a, and then you have a Rx, that means that is going to go to the next to the ester. So this is the carbon and there will be H here. So the H and there will be R, that is going to add. Again here in this ring you have a methoxy group, you have a carboxylic acid group, of course. So again, as I said, if you have a carboxylic acid group, then that is going to be the one, going to dominate the reaction. And if you have alkyl iodide, you are going to add at the end, then what is going to happen, that is going to get alkylated here. So there will be R here. If Rx equal to methyl iodide, then you end up forming the methyl here, and there will be H here, which is coming from your alcohol here. Okay. Another example here, so you have a acid and you have a OMe group. I told you that in that case what is going to happen, the acid is going to control it. It is going to form the stabilized anion, which can, after the second step, which can use with this alkyl iodide to form this compound. So here what is happening at the end, there is a H and this alkyl part is getting added in the ipso and in the para position, okay, which can be further, if you treat with the acid, then it is going to form the more stable alpha beta unsaturated carbonyl compound here. Now the final part of Bart's reduction. So we talk about the Bart's reduction of the aromatic ring. Now we are talking about alkyne. So the question comes that if you want to reduce alkyne and form a trans olefin, I think this question is getting asked in the viva and also in the exam, that if you from alkyne, if you want to get a cis, then use a palladium, and then you use palladium hydrogen, and you have to also use some poison the catalyst, correct? So that's why you have to use the Lindlar catalyst, so that can able to give you the corresponding cis, because palladium and hydrogen, in case of the palladium catalyst, the hydrogenation, both the hydrogen approaching in the same phase. But once you do Bart's reduction, you end up forming the trans, correct? So now question comes, how this is happening here. Of course, in case of alkyne also there will be single electron transfer happening from the sodium to reduce the alkyne. So there will be a dot and there will be a minus here, and in that stage, and then what is going to happen, there is a radical anion going to form at the beginning, then there will be another sodium going to give one more electron, correct? So now you can see the vinyl radical is geometrically unstable and chooses to be E to form, or the G form has electron repulsion. So what is happening, that once you are in this form, okay, once you have a radical anion formation happening, and then you got a protonation happening here, and then you give another electron. So you have this scenario here, you have this you have this electron density here, correct? So now this this vinyl radical once this formation is happening in this particular reaction, you have a electron density one side, you have a vinyl radical, correct? So last if you come to this particular scenario also, here once you give a one electron first, what is going to happen, you have a vinyl radical in one side, you have a electron density, correct? You have a so they, if they are in the Z conformation, they will be repel each other. So they don't want the repulsion. To stop the repulsion, they will arrange themselves in the E configuration. So that's how it will be, the reaction going to continue. So this is the step why your geometry getting decided, because once you are in this position, now you have a protonation here, this radical will get another reduced, you will get one more electron to get an anion, and it is going to get H. So that's how the 2 of the H is adding to the trans fashion, not in the cis fashion, because to avoid the repulsion between this radical and these electron pairs. Okay. Here is an example. Here you can see this alkyne is getting reduced here to form this corresponding trans olefin. So here in this part I talk about the dissolving metal reducing agent. You have learned some of the single electron reduction. I talk about the acetylene condensation, the Bart's reaction, and then of course the reduction for the alkyne to get to the corresponding trans olefin. Okay, I think these are the books you can follow for this part. And again, thank you so much for coming to the class, and I am going to see you guys in the next class. Thank you.